Welcome to a differential geometry class. Last class we have studied about the Gauss map, the definition of Gauss map, and spherical image definition also we have covered. Today what we are going to do is we are going to study a theorem. Theorem statement. Let S be a compact, connected, oriented end surface. Let S be a compact, connected, oriented end surface in Rn plus 1, comma, exhibited as a level set of F inverse of C of a smooth function f from Rn plus 1 to R with del f of p not equal to 0, with del f of p not equal to 0 for every p belongs to S, then the Gauss map maps S onto the unit sphere Sn. So here what is given is S is going to be a compact, connected, oriented end surface, and which can be expressed as level set of a smooth function. Then what it says is that then the Gauss map maps S onto the unit sphere Sn. In another fashion, when we are saying in terms of spherical image, a connected oriented end surface which is compact, its Gauss map or its spherical image should be the entire unit sphere Sn. So how to prove it? First we are taking a vector v belongs to Sn. Let v belongs to Sn. That means what we are going to do is this is our unit sphere. Okay, suppose this is our unit sphere is given, and here we have got the surface, so S, and you say Sn. Now we want to have from S to Sn there's a map. Exactly our Gauss map will give you the map, and we want to show in addition here is that this is onto. That means when you take a vector over here, a member in your Sn, there corresponds to a member in your S. So we are taking a member v belongs to Sn. Now consider the n plane. V perp. That means v means the space which is generated by v is of one dimension space. So when you are taking v perp, since we are dealing everything in Rn plus 1, its dimension is n plus 1. So this is a one dimensional space. When you're taking the span of v, it's one dimension. So v perp should be n-dimensional plane. So that's why we are saying that it is n-plane. V perp, consider the n-plane V perp. By moving this n-plane, far enough in the v direction, it will have null intersection with n. It will have null intersection with s. Bringing it back in until it just touches s. At some point p, comma, it will be tangent to So what does this mean is, we have taken a vector from your Sn, right? So we are having one circle over here, right, and a vector here. So this is a vector v. So when you are having v perp, means it should be like this, right? So this is our v perp. Now we want to move this v perp along the direction of v, right? So we are moving this one. So if you are moving this one, means okay, when you're moving this v perp, we can move in this direction, right? We can move here. So after moving from here to here, it will reach somewhere here. Now it have the intersection with your SS. Suppose you have got a surface over here, right? Now you move it aside. So up to here we have moved. So from up to here, then you move from here to here. So it has reached up to here. Now we have intersection with S as empty. Now you return from here to here. So somewhere it will touch us. Your S. So this point is our P. So at this point it should be tangent to 8. So we have moved this one. Oh no. Okay, let me delete this one. So in the same fashion, we can have this V perp. that is moved in opposite direction also. That means suppose we are moving this in this direction, again you will get a point here, right? From this P to, suppose you are moving from here to here, again you are moving means I will get somewhere here another tangent line, right? And suppose this point is Q. Now when you are having this normal direction here means it may come like this. This is your N of P, and when you're having this, so in the direction means this should be N of Q. So this is how we are making, we have given the description here. Okay. So hence at the point, P, your N of P, that is normal, should be equal to plus or minus V, because in this direction only it's coming. Since it should be perpendicular, it should be plus or minus V. And if your N of P is equal to minus V, then N of Q should be equal to V. Now what is Q? Where Q is obtained similarly by moving the n plane, in from the opposite direction, So we have got 2 points here. Now more precisely, consider the function g from Rn plus 1 to R defined by g of x1, x2, etc. xn plus 1 is equal to a1 x1 plus a2 x2 plus etc. plus an plus 1 xn plus 1, where your v is equal to a1, a2, etc. an plus 1. So when you're having this as p means this can be taken as v dot p, right? So this is how we are defining a function here. Now the level set of G are the n planes parallel to V perp. This can be easily checked by we know that level set is going to be, since G inverse of C, right? So this equal to set of all x1, x2, etc. xn plus 1 such that a1 x1 plus a2 x2 plus extra plus an plus 1 xn plus 1 is equal to C, right? Now if C equal to 0, if C equal to 0, what you will get? G inverse of 0 is equal to this thing, right? So it will result the points on. So this is equal to set of all x1, x2, etc., xn plus 1 such that a1 x1 plus extra plus an plus 1 xn plus 1 equal to 0. That means when you're having this such, that means this is set of all I am writing as p such that p dot v equal to 0, right? Which implies is nothing but vpub. Now we have studied about the level sets. If you go on changing this value c, you will get always parallel to this one, right? So what you're getting is the level set that we are considering should be parallel to vpub. Now since S is compact, the restriction to S, of the function g attains its extremas. Say at P and Q. That means at P it may have a minimum and maximum, and at Q it may have a minimum at P and maximum at Q, say, right? Then we have seen that it has got a extreme point. Then we can apply the Lagrange multiplier theorem. Then by Lagrange multiplier theorem, we can write your PV as some del G of P, that's equal to lambda times del F of P, right? Now this can again taken as lambda into norm of del F of P times N of P, where N is the normal, so del F of P belongs to the normal space. So you can write like this for some lambda belongs to the real number, which implies, what's the meaning of this? This V and N of P are multiples of each other, which implies your V and N of P are multiples of one another. Since both are unit length, since how we got, we have taken V from S1, that is the unit circle. So length of V should be equal to 1, and N of P, as our usual custom, we are dealing only the unit normal vector. So N of P both have the length 1. So what does this means? It follows that your N of P should be equal to plus or minus V, no other chance. Similarly, we can write N of Q is also equal to plus or minus V. So N of P equal to plus or minus V, and N of Q is also equal to plus or minus V. Now we want to check that the onto condition. So this condition cannot be sufficient. That means we want to say that when you are taken V, it should have a pre-image, right? So it remains only to check that only to check that n of q not equal to n of p, right? So if we are getting n of q not equal to n of p, means we are getting distinct inverse images, right? So we can conclude that this is onto. So we want to check n of q not equal to n of p. For this, it suffices to uh, construct a continuous function, alpha from closed level AB to Rn plus 1, differentiable at A and B such that it will satisfy two conditions. First condition is alpha of A equal to P, comma alpha of B equal to Q, and alpha dot of A equal to PV and alpha dot of B equal to QV, right? If this one condition, and second condition is alpha of T does not belongs to S for A less than T less than B. Okay, then by condition 1, if I'm selecting n equal to del f by norm of del f, so unit normal, right? Then what we are having is f composition alpha dash of A. This is equal to, by chain rule, this is del f of alpha of A dot alpha dot of A, right? Alpha dot of A. Now this is equal to norm of del f of P. Alpha of A is P, right? So del f of alpha of P can be written as del f of P into n of P dot alpha of A is PV, right? So I'm writing as PV. Now this is equal to norm of del f of P into n of P dot V, right? And similarly f composition alpha dash of B can be written as norm of del f of Q into n of Q V, right? So if n of P equal to n of Q, what will happen? Then the derivative, that means this n of Q and here you have got n of P, these two are equal, means then the derivative f composition alpha dash has the same sign at both endpoints, right? Since uh, F composition alpha of A equal to F composition alpha of B is equal to C, which implies there exists T1 and T2 between endpoints, right? We have taken that sign at both the endpoints. Now, if we can take T1, T2 afterwards, so this also we can remove it. So both the endpoints we have set. So we have said that these two have the same direction, right? Okay, we want to delete this. Okay. Okay. Now we have seen that this two is having same. Okay. Now what we are seeing is then the derivative has the same sign at both the endpoints. Now if we are selecting our normal as if n equal to minus del f by norm of del f, the same conclusion holds. The same conclusion holds because we haven't specified any normal direction here. Thus, if n of p were equal to n of q, and that's equal to plus or minus v, then f composition alpha would either be increasing at both endpoints or be decreasing at both endpoints. Now since f composition alpha of A is equal to f composition alpha of B, that's equal to C, what you are having is there exists some T1 and T2 between A and B with f composition alpha of T1 is greater than C and f composition alpha of T2 is less than C. But then by intermediate then by intermediate value theorem, there would exist a point T3 between T1 and T2 such that F composition alpha of T3 equal to C. Now this is a contradiction. What's the reason? Which is a contradiction. To our second statement. What was our second statement? If T value is lying in between A and B, then your F of alpha of T does not belongs to S, right? So condition 2. Okay. What's condition 2? Yeah, condition 1. See, condition 2 says that alpha of T does not belongs to S for A less than T less than B. So whenever T is lying between A and B, alpha of T does not belongs to S. So F of alpha of T cannot be equal to C. But here what you have got is F of alpha of T3 equal to C. So which is a contradiction to condition 2. So what you are having is, so N of P cannot be equal to N of Q, which implies the Gauss map is onto. Okay. So we have proved the theorem, and one part remaining is for us to prove is that such an alpha is existing. So we have assumed that for proving this N of P not equal to N of Q, it is sufficient to construct a continuous function, right? So we want to say that such an alpha is existing. So that we will discuss in the next class. Okay, so today we have stated the Gauss theorem, that is, let S be a compact connected oriented n surface in Rn plus 1 exhibited as a level set F inverse of C of a smooth function f from Rn plus 1 to R with del f of P not equal to 0 for every P belongs to S. Then the Gauss map maps S onto the unit sphere Sn. So hope you understood the proof. If you find any difficulty in understanding this, please feel free to ask me. Okay, so thank you for your patient listening. Thank you.